Alright, so we're going to talk about Chapter 10, Section 2, two population means with a known standard deviation. Alright, so this is when we know the population standard deviation. Alright, so if we go to our flowchart, we're still going to be doing the hypothesis testing, but now we're doing a mean. We know the standard deviation, so we're doing a z-test for this. So example 10.7. An interested citizen wanted to know if Democratic U.S. senators are older than Republican senators, on average. Okay, so Democratic senators older than Republican senators. So we have the 61.675 years for their mean, 10.17 years for their standard deviation, 30 were selected. 61.704 years for the mean, and then standard deviation of 9.55 years. So the information for the Republicans was given first, and we're asked to find if the Democratic senators are older than Republican senators, on average, and a test at 5% level of significance. All right, so we're going to do our test, and this is going to be a two-sample z-test. So we know on this one that it's going to be the two-sample t-test, because we do not know the standard deviation for the population. We have them for the samples, but not for the population. All right, so we're going to do this from the statistics. So we have our first group that we're going to enter our data in for, and then our second group that we're going to enter our data in for. So for our first group, we have the 61.675 and the standard deviation of 10.17, sample of 30. Then for the second group, 704 and standard deviation of 9.55 with a sample size of 30. All right, so when you do this, you're going to find that your p-value is higher than the alpha. So if the p is high, the null must fly. All right, so p if high, the null must fly. All right, so let's take a look at 10.3, comparing two independent population proportions. So now we're going to do two independent population proportions. So we're still going to go through and use our flowchart. This is a hypothesis test, but we're doing a proportion. You can go through and do your required checks and see that it's binomial, it's a random sample, and that the test, for the test part, we have n times p is greater than or equal to 5, and n times q is greater than or equal to 5. So p is the probability of success, and q is the probability of failure. All right, so this is telling us we're going to use not the one, but the two-sample proportion z-test. So the two-sample proportion z-test. All right, so if we do example 10.8, we have two types of medications for hives are being tested to determine if there's a difference in the proportion of adult patient reactions. So 20 out of a sample of 200 adults given medication A still had hives after 30 minutes after taking medication A. Okay, so 12 out of another sample of 200 given medication B still had hives after taking the medication. So we're going to test this at a 1% level of significance. All right, so this is a proportions, and we are comparing our two groups, the medication A and medication B. So medication A is group 1, medication B is group 2. All right, so we know we're doing a test of two proportions, group A and group B. So when we look at our null hypothesis, the null hypothesis says that they are equal, that there's no difference between the two groups. Okay. Then we have to take the difference and say that when you subtract them, that's going to equal 0. So if they are the same, that's going to equal 0. All right, so if they're the same, that equals 0. If we look at our alternate hypothesis, they're not going to be equal to each other. And if they're not equal to each other, they're not equal to 0. All right, this is going to make it two-tailed. All right, so we go to our two proportion z-test, put in our information. We had 20 out of the 200 for group A and 12 out of the 200 for group B. So our 20 out of the 200 and 12 out of the 200 for each group. And we're just comparing to see if they are not equal. They're not the same. This is a two-tailed test. All right, so we go through and we calculate that, and our p-value is 0.14037. Okay, So 14037. So when we take that and we can compare it to our alpha, that's going to help us decide. So if our p-value is that, our alpha value, we're doing this with a 1% level of significance. The p-value is higher than the alpha, so if p is high, the null must fly. That means when we look at this, the p-value being higher means that we do not reject the null hypothesis. So at a 5% level of significance from the sample data. So now we've got the two-tail on this one. Half of it goes on each side. Okay? And, oh, I used the wrong one. So now we've got the at 1%, so we do not reject the null. At a 1% level of significance from the sample data, there is not sufficient evidence to conclude that there's a difference in the proportion of adult patients who did not react after 30 minutes to the medication A and medication B. So there's not sufficient evidence. All right, so 10.4. Now we're going to look at matched or paired samples. All right, so matched or paired samples. These are the dependent ones. So there are some criteria on this. So the first, we have simple random samples being used. Okay, our sample sizes are often small. And this third one, this is the big one. The two measurements or samples are drawn from the same pair of individuals or the same objects. Okay, so two different measurements from the same things. Their differences are calculated from the matched pairs, and the differences are used for the hypothesis test. All right, so we take a look at this one. We're looking at the study conducted to investigate the effectiveness of hypnotism in reducing pain. All right, so we have the before and an after for all of these different subjects. So this makes it a match. We're taking the same taking measurements from the same person. So the before and the after. Before and after. All right, so if you look at before, that's before the hypnosis, and that's after the hypnosis. All right, now we're going to do the test with 5% significance level. Now to do this, we're going to use the difference. So we're going to take the after data and subtract it from the before data. So after minus the before. So 6.8 minus the 6.6 gives us the difference of 0.2. And we're going to use those differences to do our calculation. So we use the differences for this calculation. All right, so we take all of that information and we're going to use the differences. If they're negative, that means that the hypnosis decreased the level of pain. Okay, if they're positive, that means it increased the level of pain. So you do the after minus the before to get our differences. All right, so our null hypothesis says that it's going to be greater than or equal to 0. Okay, that means that there's the same or more pain felt after hypnotism. Okay, so they had the same or more pain after being hypnotized. Right? The alternative is that it's less than 0. Okay, and in this situation, that means that there's less pain felt after hypnotism. So we're going to go to our list and, our test. We're going to be using a t-test on this because we don't have the sample standard deviation, so it's a t-test. And we've got our information in the list on this one. So in list 1, I've put all those differences in there. Now, you could put in list A, but the after, the before, and then the difference. So if you do after minus the before, that would equal, so after minus the before equals the difference, and then you could use that. I just chose to do the differences. So if we put that in and then do our test, now I'm going to go from the data instead of stats. So we want it to be equal to 0, meaning that I had no change. And then our list is list 1. My frequency is also 1. And I'm going to check to see if this is less than, so that to see if the hypnotism had effect on the pain. Okay. So when we do this, we get 0.009478. Okay. So that's our p-value. So 0.0095 when we round it is our p-value. Now this is to the left because it's less than. So this is a left-tailed hypothesis test. So 0.0095, we're going to take that and compare it with our alpha to help us make a decision about this hypothesis test. So if our p-value is going to be less than a, our alpha, we reject the null. So that means that at a 5% level of significance from the sample data, there is sufficient evidence to conclude that the sensory measurements on average are lower after hypnotism. In other words, hypnotism appears to be effective in reducing pain. So being hypnotized helps to reduce the pain. All right, example 10.1.3. This one's talking about comparing dominant hand versus weaker hand. So once again, we know this is going to be a matched pair because we have two measurements from the same person or the same object. We have the weaker hand and then we have the dominant hand. And we're going to be using the differences. So we record the differences. So I've got 30 and the 28. So that difference is going to be 2. So a 30 minus the 28 is 2. And let me move this down a little bit. So the 2 comes from that difference. Then we have 12, 7, -1, 2, 0, and then 4. So those are the differences between the dominant hand and the weaker hand. So we use those differences, and I put those into my list. Now I could use the data setting on this, but I'm going to use do the variable statistics on this to show you how you can get that. So we do our 5-number summary stats, or the one variable statistics. So the mean is given and the sample standard deviation. So we have our sample mean and our sample standard deviation. Okay, and that's going to be the same that's in the packet. So 3.71 and 4.5 when we round. So then I can go in and put that into the calculator, and we get our p-value of 0.0358 on each side, because it's going to get evenly split because this is two-tailed. And now it comes to the decision time. So we're going to compare this to the our p-value to the alpha 5% level of significance. So the p-value is greater than alpha. So if the p-value is high, we fail to reject the null.